Scientists and physicists have always been fascinated by the universe and the phenomena that it reveals, but one thing has kept them sitting at their research desks for years: antimatter. When scientists previously spoke about antimatter, they had very little to discuss, because antimatter is one of the strangest things in our universe. However, a recent discovery has been made by scientists, which is not only poised to change our perspective, but also to explain the mystery behind antimatter. Come with me to unravel the most incredible situations that arise in the world, in space, or in other dimensions. You are on Awake. Subscribe to the channel, like and share the video on your social media. This is the most sincere and free way to value my hours of research and production. The existence of antimatter was confirmed in 1995 by a team of scientists from the University of California, Berkeley, who were awarded the Nobel Prize 4 years later. Antimatter is capable of destroying our universe when exposed to common matter, as they annihilate each other. Although this destruction is mysterious, it has its own associated benefits. When matter and antimatter collide, they release powerful energy, enough to power a light bulb or even a city. Although antimatter has been a widespread topic in science fiction stories for several decades, it is real and deeply rooted in modern scientific theory. But what exactly is antimatter? It is like matter, but with different properties and charges, capable of destroying matter when they come into contact. Despite its benefits, antimatter is still a mystery to science, and physicists are still researching ways to harness its energy. All attempts have been unsuccessful so far, which further proves why antimatter is one of the mysteries of the world of science. For generations, antimatter refers to particles similar to the familiar matter we know. But such antiparticles have the same mass as their sibling particles, yet remain their opposites in some aspects. To give you an idea, an electron, also known as a positron, has the same mass as a regular electron but a positive charge opposite to the normal electric charge of the electron. Antimatter was initially predicted by British physicist Paul Dirac in 1928 when he attempted to combine quantum mechanics, which explains subatomic particles, and Albert Einstein's theory of relativity. Dirac was examining solutions to an equation that best describes the motion of an electron moving close to the speed of light. Just as the equation reads x squared equals 4 can provide two possible solutions, x equals 2 or x equals -2. Dirac's equation could have two solutions, one for an electron with negative energy and another for an electron with positive energy. According to the European Organization for Nuclear Research, initially Dirac was reluctant to share his findings with the public, but he eventually accepted and posted that every particle in the universe should have a mirror image particle that acts like it but has an opposite charge. A few years later, positrons were found by physicist Carl Anderson of the American Institute of Technology in California on August 2, 1932. Anderson was the first to detect the first antimatter particle. The discovery of the positron was unexpected, as Anderson had no intention of looking for antimatter. He had built a cloud chamber to find the composition of cosmic rays and high-energy particles. In 1932, an instrument of Anderson's fell from space and was recovered. It consisted of a magnet that allowed the determination of the charge of particles passing through it, as well as a lead plate that slowed down the particles. Anderson took several photographs of the tracks left by cosmic ray particles, but one of them intrigued him. The trajectory curve of this particle showed that it was positively charged, but much less massive than a proton. An editor of the physics journal suggested that this particle was the positron, a theory that had already predicted its existence in 1931. Anderson did not realize until later that the positron was similar to the electron, except for its opposite charge. This discovery earned him and Dirac the Nobel Prize in Physics in 1936. Antimatter is occasionally produced in particle accelerators and occurs through the collision of high-energy particles in the Earth's atmosphere. However, the mystery of antimatter is hidden in the depths of its marked absence. As far as scientists can tell, the universe around us is mainly made of matter without antimatter, which confuses scientists. They continue to study theories around the beginning of the universe, also known as the Big Bang. The Big Bang theory was developed in the early 20th century to explain observations that visible galaxies are moving away from the Earth in all directions, leaving two possible interpretations: either the world is at the center of a cosmic explosion or is expanding. Galaxies in space are expanding in all directions. This explanation is more accepted by science today, as the effect is similar to stretching an elastic band or inflating a balloon. The marks on the surface of the material move away not because of the relative movement of the points, but because the space in which they exist is moving away. Before the birth of the universe, everything was denser, hotter, and closer. It is possible to imagine how hot it was by looking back millions or billions of years. The universe expanded as it cooled, and quantum fluctuations of light created pairs of electrons and positrons, which are particles and antiparticles. Some of these particles were created and destroyed almost immediately, but others accumulated to form stars, planets, atoms, and everything we see around us today. However, an equal amount of antimatter must also have been created, but we do not know where it is or what it is transformed into. Scientists are working hard to solve this mystery. They are trying to create antimatter particles using ultra-high-speed collisions in particle accelerators, such as the Large Hadron Collider located in Geneva. This is one of the most central questions of modern cosmology, and many scientists are dedicating their efforts to finding a solution. Galaxies in space as a whole are expanding in all directions. The explanation of space expanding everywhere seems to be the most justifiable and has been widely accepted in science. The effect is similar to testing the ability of a rubber band or inflating a balloon. The marks on the surface of the rubber will move separately, not due to the relative movement of the points along the rubber, but because the space in which they exist is moving away. Before the universe was born, things must have been denser, hotter, and much closer. We can imagine how hot the universe was by looking back millions or billions of years. In fact, it is relatively simple to figure out when everything must have been a little over 13.8 billion years ago when the universe began to expand as it cooled. The quantum fluctuations of photons in this plasma continually created pairs of electrons and positrons, particles and antiparticles. Some of these particles were created and destroyed almost immediately. But as the plasma continued to expand and cool, some antiparticles also were created but not annihilated. These particles are the ones that mainly accumulated to form the stars, planets, atoms, and everything we see around our universe today. However, the question of where the antiparticles went or what they formed into remains one of the biggest mysteries of modern cosmology. Scientists are working hard to solve this puzzle in an attempt to find a solution to this mystery. Scientists have gathered to create antiparticles using ultra-high-speed collisions in colossal particle accelerators such as the Large Hadron Collider located outside Geneva and operated by the European Organization for Nuclear Research. One experiment led CERN scientists to create antihydrogen, the most complex antimatter element produced to date. Although antimatter is produced in various experiments at CERN, the produced antiparticles cannot be trapped due to their very high energy, which causes them to harmlessly destroy themselves in the detectors. And even when produced, they are produced in very small amounts, to the point that even if CERN uses its accelerators only to make antimatter, it cannot produce more than about a billionth of a gram per year. Furthermore, the efficiency of producing and storing antimatter is very low. About 1 billion times more energy is needed to produce antimatter than is eventually contained in its mass. This means that with its low production efficiency, it would take 25 million kilowatt-hours to produce just 1 gram of antimatter. What's your opinion on the intriguing antimatter? Leave your comment, share your opinion. Until the next video.